Welcome to Digital Learning, Department of Collegiate Education. I am Dr. Latha Devi Puli, Assistant Professor, Department of Mathematics. In this video, we discuss about integral calculus of first semester BSc Mathematics. This is the continuation of the previous video, that is the Leibniz rule. The learning objective of this session is to understand the concept of Leibniz rule of differentiation under integral sign and to verify that to the given integrals. By the end of this session, the student will be in a position to understand the concept of Leibniz rule of differentiation under integral sign and able to verify the given integrals. The prerequisites for this topic is the concept of the partial differentiation and Leibniz rule. Now, in the previous session, we have done the problems based on the Leibniz rule. Let us recollect the Leibniz rule once again. If phi of alpha is equal to integral of a of alpha to b of alpha f of x comma alpha into dx, where a and b are functions of alpha, where alpha is the parameter, then the Leibniz rule is d phi by d alpha is equal to integral of a of alpha to b of alpha dou by dou alpha of f of x comma alpha into dx plus d by d alpha of the upper limit b of alpha into f of b of alpha comma alpha minus d by d alpha of a of alpha into the lower limit of the integral into f of a of alpha comma alpha. That means the lower limit of the integral comma alpha into alpha. This is the formula when the limits of the integration are the parameter, are in terms of the parameter. When the limits of the integration are constants, in such a case, the Leibniz rule will become d phi by d alpha is equal to integral of a to b dou by dou alpha of f of x comma alpha into dx, because a and b are constants. So d by d alpha of constant will become 0. So this complete term will become 0, and d by d alpha of a is a constant. This term also becomes 0. So this complete term becomes 0. Hence the above formula reduces to this form. And in this session, we are going to discuss about how to apply Leibniz rule for the problems which involves the constant limits. So in all the problems, we will be applying this formula. Now let us discuss about the problems. This is section 40, integral calculus, problems on Leibniz rule. The first problem is like this. Using Leibniz rule of differentiation under integral sign, evaluate integral of 0 to 1 x to the power alpha minus 1 by log x into dx, where alpha greater than 0 is a parameter. Hence find integral of 0 to 1 x cube minus 1 by log x into dx. Here the given integral, whatever we have to evaluate, is from 0 to 1 x to the power alpha minus 1 by log x into dx. So this I will be taking as phi of alpha. So for phi of alpha is equal to integral of 0 to 1 x to the power alpha minus 1 by log x into dx. Now we can't evaluate this integral by known methods. That's why we have to evaluate Leibniz rule. So what is Leibniz rule? The Leibniz rule says that d phi by d alpha is equal to integral of a to b dou by dou alpha of, that means for this integrand we have to do the partial differentiation, dou by dou alpha of f of x comma alpha. So d phi by d alpha is equal to integral of 0 to 1 dou by dou alpha of this function, dou by dou alpha of x to the power alpha minus 1 by log x into dx. That is equal to integral of 0 to 1 partial differentiation of x to the power alpha. So log x will be treated as constant here. So 1 by log x into the partial differentiation of x to the power alpha will be in the form of a to the power x. So x to the power alpha into log x into dx is the formula, and differentiation of minus 1 will become 0. That's why we will be getting x to the power alpha into log x into dx. Already log x is there in the denominator, and log x here, these two terms gets cancelled, and we will be left with integral of 0 to 1 x to the power alpha into dx. Now for this apply the integration. This is in the form of x to the power n. We are doing integration with respect to x, so alpha is treated as constant here. So the integration of this will become x to the power alpha plus 1 by alpha plus 1 from 0 to 1. If you apply the limit, upper limit is 1 to the power alpha plus 1, which is nothing but 1, minus 0 to the power alpha plus 1, which is nothing but 0. So 1 minus 0 is 1, divided by alpha plus 1 is written as it is. So d phi by d alpha is equal to 1 by alpha plus 1. But we have to find out the value of phi. So integrate this step on both the sides with respect to alpha, so that we will be getting phi of alpha is equal to 1 by alpha plus 1 into d alpha, it is d alpha. So that we will be getting integral of 1 by alpha plus 1 is nothing but log of alpha plus 1 plus c. But we have to find out this c value. To find c value, the given problem is from 0 to 1. That's why I will be substituting alpha is equal to 0 in equation number 1. That is, equation number 1 is nothing but the given problem. So if I substitute alpha is equal to 0, I will be getting phi of 0 value as integral of 0 to 1 x to the power 0. X to the power 0 is 1 minus 1. X to the power 0 is 1. 1 minus 1 is 0. So integral of 0 is 0. So phi of 0 is equal to 0 we will get. So in this final answer, I will substitute alpha is equal to 0, so that I will be getting phi of 0 is equal to log of alpha is 0 plus 1 is log 1. Log 1 is 0. So phi of 0 is equal to log 1 plus c we will get. But log 1 is 0. So, and already as we already discussed, phi of 0 is equal to 0. So substitute that phi of 0 value here. So phi of 0 becomes 0 is equal to 0 plus c. That applies to c is equal to 0. Hence, phi of alpha is equal to log of alpha plus 1. Hence, phi of alpha is equal to integral of 0 to 1 x to the power alpha minus 1 by log x into dx, that is equal to log of alpha plus 1. But the problem is given as find integral of 0 to 1 x cube minus 1 by log x into dx. This is the final answer we got. But by observing this with the final answer, in place of alpha we have cube 3. That's why in this final answer put alpha is equal to 3. So that we will get integral of 0 to 1 x cube minus 1 by log x into dx is equal to log of 3 plus 1, that is equal to log 4. Therefore, integral of 0 to 1 x cube minus 1 by log x into dx is equal to log 4. Now, let us see the next problem. Using Leibniz rule of differentiation under integral sign, evaluate integral of 0 to infinity tan inverse of alpha x by x into 1 plus x squared into dx, and hence find integral of 0 to infinity tan inverse of x by x into 1 plus x squared into dx. Now, by using Leibniz, and first of all we have to see what are the limits here. The limits of integration are 0 and infinity, which are constants. So the Leibniz rule for constant integration is d phi by d alpha is equal to integral of a to b dou by dou alpha of f of x comma alpha into dx. So here let us take the given problem as phi of alpha. So let phi of alpha is equal to integral of 0 to infinity tan inverse of alpha x by x into 1 plus x squared. Since we have x in the numerator as well as in denominator, we can't evaluate this integral by direct methods. So we will be applying Leibniz rule here. So by using Leibniz formula, we have d phi by d alpha is equal to integral of 0 to infinity dou by dou alpha of f of x comma alpha, which is nothing but tan inverse of alpha x by x into 1 plus x squared into dx. That is equal to integral of 0 to infinity dou by dou alpha of. So we have to treat only alpha as variable and x will be treated as constant. So this 1 by x into 1 plus x squared is constant written as it is, into integral of tan inverse of alpha x is 1 by 1 plus x squared, means alpha x whole square, into differentiation of alpha x with respect to alpha. It is differentiation of alpha is 1 into x is written as it is. And here we have x in the numerator as well as in the denominator. So both gets cancelled and we will be left with the integral of 0 to infinity 1 divided by 1 plus x squared into 1 plus alpha squared x squared into dx. Now by using partial fractions we can express this product of two functions as sum or difference of these two functions like this: 1 by 1 minus alpha squared into 1 by 1 plus x squared minus alpha squared by 1 plus alpha squared x squared, with the limits of the integration as 0 to infinity. Since we are doing integration with respect to x, 1 by 1 minus alpha squared is constant, bring it out. Integral of 0 to infinity 1 by 1 plus x squared minus alpha squared by 1 plus alpha squared into x squared, that is equal to 1 minus 1 by alpha squared into integral of 1 by 1 plus x squared is tan inverse x minus alpha into integration of 1 by, this can be written as alpha x whole square, so that this is in the form of 1 by 1 plus x squared, which is nothing but tan inverse of alpha x by alpha. So alpha squared and 1 alpha will get cancelled and we will be left with 1 alpha into tan inverse of alpha x from 0 to infinity. Here nothing is given about alpha, whereas in the previous problem, in the first problem, it is mentioned that alpha is greater than 0, but here nothing is mentioned about alpha. And since this is tan inverse problem, we have to discuss about two cases, that is when alpha is greater than 0 and when alpha is less than 0. So when alpha is greater than or equal to 0, d phi by d alpha is equal to, this is what the limits we got. So 1 by 1 minus alpha squared into tan inverse of upper limit infinity is pi by 2 minus tan inverse of 0 is 0. So not written anything, minus alpha into tan inverse of the upper limit infinity is pi by 2 minus tan inverse 0 is 0. In these two terms pi by 2 is constant, bring it out common. So pi by 2, if I bring out, I will be left with 1 minus alpha by 1 minus alpha squared can be written as 1 plus alpha into 1 minus alpha. So that 1 minus alpha, 1 minus alpha will get cancelled and we will get d phi by d alpha is equal to 1 divided by 1 plus alpha into pi by 2. But we have to evaluate or we have to find phi value. We got d phi by d alpha value here. So integrate this function with respect to alpha on both the sides. So that integral of d phi by d alpha into d alpha is equal to integral of 1 by 1 plus alpha into pi by 2 is constant written as it is into d alpha. That implies to phi is equal to pi by 2 is constant, bring it out. Integral of 1 by 1 plus alpha is log of 1 plus alpha plus constant of integration c1. Next, in the same way, if alpha is less than 0, same step we will get here, but 1 by 1 minus alpha squared into tan inverse of infinity is pi by 2 minus alpha into tan inverse of minus infinity it will become, because alpha is less than 0, right? So when alpha is less than 0, it will become tan inverse of minus infinity by applying the upper limit. That's why tan inverse of minus infinity is minus pi by 2. So minus alpha into minus pi by 2 we will get. So minus into minus gets cancelled, means minus into minus becomes plus. So pi by 2 into 1 plus alpha by 1 plus alpha into 1 minus alpha. So in this case 1 plus alpha, 1 plus alpha will get cancelled. We will be left with d phi by d alpha is equal to 1 by 1 minus alpha into pi by 2. But we have to find phi value. So by integrating with respect to alpha, we will get integral of d phi by d alpha is equal to integral of 1 by 1 minus alpha into pi by 2 into d alpha. That implies to phi is equal to pi by 2 into integration of this 1 by 1 minus alpha is 1 by log of 1 minus alpha plus c2 with negative sign here. We will be getting negative sign here, where C1 and C2 are constants to be found by substituting phi of 0 is equal to 0. So we will get phi of alpha is equal to integral of 0 to infinity tan inverse of alpha x by x into 1 plus x squared into dx, that is equal to pi by 2 into log of 1 plus alpha plus c1 if alpha is greater than or equal to 0, that is equal to minus pi by 2 into log of 1 minus alpha comma when alpha is less than 0. The third problem is using Leibniz rule of differentiation under integral sign, evaluate integral of 0 to infinity e to the power minus x into sine of alpha x by x into dx, where alpha is greater than 0 is a parameter. Here alpha is greater than 0, so we need not discuss two cases. One case is enough for this problem. So, and we know that the limits of the integration, here the limits of the integration are constants. So, we will apply this formula as the Leibniz formula, that is d phi by d alpha is equal to integral of a to b dou by dou alpha of f of x comma alpha. Now, here we can't evaluate this integral by direct integration. So, let us apply Leibniz formula, that is d phi by d alpha is equal to integral of 0 to infinity dou by dou alpha of e to the power minus x into sine alpha x by x into dx. First, we have to do partial differentiation with respect to alpha. So, e to the power minus x by x is constant. Differentiation of sine alpha x with respect to alpha is cos of alpha x. Here alpha with respect to alpha we are doing, so x is treated as constant, so we will get into x into dx. So that x and x will get cancelled and we will be left with integral of 0 to infinity e to the power minus x into cos alpha x into dx. Now we are having one formula, that is integral of e to the power ax into cos bx into dx is equal to e to the power ax by a square plus b square into a cos bx plus b into sin bx. By applying this formula, here we will get e to the power minus x is here. So, e to the power minus x by minus 1 whole square plus coefficient of x is alpha. So, alpha square into a cos bx. A is minus 1 here, minus 1 into cos alpha x plus b. B is nothing but alpha sin bx, alpha x. Integration is evaluated. So, 0 to infinity limits we have to apply. So, written on right side. That implies to d phi by d alpha is equal to 1 divided by, apply the upper limit, e to the power minus infinity is 0. 0 into anything will become 0. So, upper limit is 0 minus, if you apply the lower limit, e to the power 0 is 1. So, 1 into cos 0. Cos 0 is 1. So, minus 1 and this term will become 0. So, 1 divided by 1 plus alpha squared. 1 by 1 plus alpha squared is constant into 0 minus of minus 1, that is equal to 1 by 1 plus alpha squared. This is our d phi by d alpha, but we have to find phi value here. So, by integrating on both the sides, we get phi is equal to integral of 1 by 1 plus alpha squared is tan inverse alpha. Therefore, integral of 0 to infinity e to the power minus x into sine alpha x by x into dx is equal to tan inverse alpha. So, with this, we have completed the problems on Leibniz formula, where we can't, by using Leibniz formula, we do the problems of finding integration for which we can't find the integral by direct methods. So, the references are Santinarayan and P.K. Mittal, Integral Calculus, preprint, New Delhi, S. Chand and Publications, published in 2013. G.K. Ranganath, BSc Mathematics for first semester, S. Chand and Co. Private Limited. G.B. Gurrajachar, Mathematics BSc first semester, Academic Excellence Series Publications 2014. Thank you.